Jon Keating from the University of Bristol, speaking on quantum chaotic resonance eigenfunctions.
Okay, thank you, and thank you to the organisers for the invitation. This will follow on rather naturally from the last talk, although rather different in spirit. Rather different in spirit. It concerns resonance eigenfunctions in open systems where the classical trajectories are hyperbolic. What I want to say in this case is basically we know so little that most of the content of the talk will be a statement of problems, very few of which we can solve, but some of which fortunately we have been able to make some very modest progress on very recently. So much the most interesting part of the talk will be the problems. What I can say that's new will be, as I say, rather modest, but hopefully the first steps to these in attacking these rather interesting problems. So concerning resonance eigenfunctions, and most of the talk will be background, explaining what the problems are, and in particular drawing a comparison with closed systems where we know a huge amount and have done for a very long time. So this is joint work with Marcel Novaes, Sandra Prado and Martin Zieber, and that was work that appeared a couple of years ago. And then very recently I have some work with Stefan Nonnenmacher, Marcel Novaes and Martin Zieber. So I'll be describing what's in those papers. So let me start by telling you about closed systems, so cases where we know a huge amount and have done for a very long time, and most of us learnt this stuff when we started as PhD students. And I should apologise, by the way, first of all, I didn't intend to give a Blackboard talk, these were my notes for the Blackboard talk, but I'm horribly tired, and I feared I'd go so slowly I wouldn't get to tell you anything new at all, which comes at the end of the talk, so I decided to scan them in. But I will go through these slides rather slowly, and we'll also write on the blackboards. So in closed systems, we have Schrödinger equation, which I'll take to describe a discrete spectrum of energy levels En and eigenfunctions psi n. And just for later purposes, analytically, one can describe the eigenvalues and eigenfunctions in terms of the green function, the integral kernel of the resolvent operator. So the eigenvalues are the poles of the green function, and the eigenfunctions are related to the residues at the poles. Now, so we've known a lot about the eigenvalues and eigenfunctions in this case for a very long time. In particular, we know the large-scale structure of the counting function, for the eigenvalues. That is, we know if we have eigenvalues, in this case, are real, and we count the number in a very large range, we have a rule for doing that, which essentially goes back to Hermann Weyl about 100 years ago now. This is Weyl's law, which is the following: that the number of eigenvalues up to some energy E scales like 1 on Planck's constant to the power d. These are the number of degrees of freedom in the system. So that's an integer power of 1 on Planck's constant. And the energy dependence is contained within this term, which is the volume contained within the energy shell, the surface of constant energy in phase space. So this surface will play a very important role in what I want to say. I want to draw attention to it. It's important because it's an invariant set of the classical mechanics. So the surface of constant energy doesn't change under the classical mechanics because energy is conserved. And it's the largest such set in phase space. There are other sets of points in phase space which are invariant, for example, those lying on periodic orbits, but they lie within this larger set. So this plays an important role. It determines the large-scale structure of the counting function for eigenvalues. So the famous example is that of billiards in d dimensions, and this was the case studied by Hermann Weyl, where if one has the Helmholtz equation inside some domain with appropriate boundary conditions, for example, Dirichlet, the counting function for the eigenfrequencies in this case is just determined by the volume of the domain and the kth power, the dth power of k, the wave number. So this is all, I believe, well known. But I'm reminding you of it because I want to draw the distinction later on with the case of resonances. The second thing we know concerns not the eigenvalues but the eigenfunctions, their large-scale structure. So for the eigenvalues, we know the structure on scale large compared to the mean eigenvalue spacing. That's Weil's law. And for eigenfunctions, we know a great deal about their structure on scales large compared to the de Broglie wavelength. And this is contained within a set of theorems which go under the name of quantum ergodicity. And these go back to Schneelmann, Steve Zeldich, Colin de Verdier, etc. And it can be stated as follows. If you have a system where the classical flow is ergodic, so classical trajectory is ergodic on the surface of constant energy, then the quantum wave functions are, in a sense, ergodic. And I'll make that sense precise now. The sense is the following. If you represent the eigenfunctions in phase space, for example, by means of the Wigner function, the Fourier transform of the autocorrelation function of the wave functions, then the Wigner functions, so representations of the eigenfunctions in phase space, Wick-Star converge in the semi-classical limit to the microcanonical distribution, that is, the delta function on the surface of constant energy. So essentially, quantum wave functions condense onto the surface of constant energy. Now, this is no surprise. I emphasize again, this surface of constant energy is the natural invariant set in phase space. It's time independent. And so it's natural that that's the surface that supports time independent quantum measures, for example, measures as generated by quantum eigenfunctions. So quantum eigenfunctions uniformly spread on the invariant set of points in phase space, the largest such yet, which is the surface of constant energy. So for example, for billiards, this is very straightforward. If we have our billiard domain and we have our eigenfunctions and we ask what's the mass within some subregion, little gamma, then the mass is just the volume of this subregion divided by the volume of the total billiard. In this sense, the quantum eigenfunctions are ergodic. Now I emphasize that this, I should emphasize rather, that this convergence is rather interesting. There are many ways one can take the limit of a sequence of states. For example, here the sequence of states as the index n tends to infinity, or more generally, in the example, in the general statement above, we're considering a sequence of eigenvalues whose energies converge to some energy E, whose values converge to some energy E in the semi-classical limit. There are many ways one can take such a limit. And these theorems hold for subsequences of density 1 amongst all possible subsequences in the semi-classical limit. So there might be exceptional subsequences. So if you pick a subsequence at random with probability 1, this will be the limit, the microcanonical distribution. However, there may be some subsequences where the eigenfunctions converge to something else. For example, they may lie on periodic orbits. And that's not excluded by these theorems. This is the question which was raised by, I think, first by Rudnick and Sarnak in a precise mathematical way, of quantum unique ergodicity. That is it the case that these limits hold for all subsequences? Can one exclude the possibility of there being exceptional subsequences which converge to some other limiting measure? Well, this is a remarkably interesting question. It turns out that there are some systems where one can prove quantum unique ergodicity, no exceptional subsequences, and other systems where one can prove that unique ergodicity fails. And it's not at all clear what the general conditions are which guarantee uniqueness of quantum ergodicity. Is there a question?
Yeah, so you're taking a sequence of eigenfunctions and then you're doing an integral on them and you're finding
Yes.
that the integral somehow is
Yes.
controlled by the constant energy surface?
Exactly.
What, could you just say, is that a momentum space integral that you're doing?
At the top, the definition of the Wigner function is the position space integral. So it depends on the momentum. It's a Fourier transform, and the momentum appears as the Fourier conjugate variable to the correlation distance in the autocorrelation function. So it's not at all clear when unique ergodicity holds, and it's a very interesting open question. So this has been recently addressed by some very interesting work of Lyndon Strauss and Nonna Masher and co-workers. They're very interesting open questions here. But I'll return to this later when we get back to resonance eigenfunctions. Well, I've given you some examples involving billiards. There's another interesting class of examples which I want to describe for later purposes. And these are torus maps. So rather than dealing with billiards, which are rather, as I'll say, too hard for us to prove anything for rigorously when it comes to resonances, I want to turn to quantum maps which are intrinsically simpler. So a map, we'll think of a map of the two torus onto itself, and we'll think of the two torus as representing a phase space. So there are two coordinates, position and momentum, on the torus. It's a phase space, and we'll think of maps acting on that phase space which are symplectic. So they form a natural representation of classical mechanics. And for 2 dimensions, symplectic just means area preserving. So we have this area preserving map M, and we'll think of it will turn out that we want to look at examples which are strongly chaotic hyperbolic. So for example, the Arnold-Cat map or the Baker map. That's the classical mechanics. Quantum mechanics, I won't describe in detail. I'll just tell you the results of a rather involved theory. Since the phase space has finite volume, the quantum Hilbert space is finite dimensional. And the dimension of the Hilbert space it plays the role of 1 on Planck's constant. Quantum dynamics is then generated by unitary transformations acting on this finite dimensional Hilbert space. So unitary matrices of dimension n. And the art of quantization is to find a unitary matrix which in some sense quantizes the classical symplectic transformation M. And what one means by quantization is one finds a unitary matrix which acts in the semi-classical limit as n tends to infinity on smooth distributions in phase space, acts on them classically in the same way that M acts on classical points in that phase space. So that's not a unique process. Quantization is not a unique process, but one can work backwards. Given a matrix U, one can test whether it represents a quantization by looking at it in the semi-classical limit.
Can I ask you a question?
Yes.
Here, just before I switch? Well, for existence of maximum momentum, that is it important here? Because the reason I'm asking is that if it's not, then if you equally distribute energy through the infinite Fourier space, it's infinite energy. So
They equidistribute on the surface of constant energy E. So it's not infinite energy, it's constant energy.
right, but but you want it uniform and more of your on the energy equal to constant surface.
Yes.
Right? And
Yes.
so each so you this means, well, say if your if your number of modes is infinite, then each mode gets only 0 energy.
No, it's not that this is saying that the sum over all modes converges in this way. It's saying that if you consider a sequence of modes, they individually converge to being uniform on the surface of constant energy. So I think it's perfectly well defined. They have energy E. Each mode has energy E in the limit. So let me give you an example. And this is an example I shall be using later on. This is the triadic Baker map. So we start with our torus, which I'll represent as the unit square, and I'll split it into 3 sections, 3 rectangles of height 1 and width 1/3. And the map acts in the following way. You squash the unit square uniformly down, vertically, by a factor of 3, and you stretch horizontally by a factor of 3. So you get 3 new rectangles now, whose height is 1/3, and each of whose widths is 1. You get the second rectangle and place it on top of the first, and the third rectangle and place it on top of the second. So this is now an area-preserving map of the unit square back onto itself, but it's uniformly hyperbolic. All points vertically have been squashed by a factor of 3 and horizontally stretched by a factor of 3, so it has Lyapunov exponent log 3. So this is a famous simple example of a strongly chaotic dynamical system. The quantum map corresponding to this transformation, it can be written down straightforwardly, and this was first done by Andrei Vouros and Marcus Saraceno. So if the dimension of the Hilbert space is divisible by 3, then the unitary transformation in question is just a matrix of block diagonal form where each block is a finite dimensional Fourier transformation. So this is rather natural structure. This is representing the fact that up in the classical transformation, the block on the left went to the bottom. Every point here in the rectangle shaded blue has gone to the rectangle shaded blue on the bottom classically. Likewise, the middle has gone to the middle, and the right has gone to the top. And that's why the off-diagonal elements here are 0. So this term represents left goes to bottom, middle goes to middle, right goes to top. And the Fourier transform is very natural because semi-classically the Fourier transform just generates dilation. And this map is piecewise linear. So this is the natural quantization of that classical transformation. And now this is a unitary matrix, so its eigenvalues lie on the unit circle. And Weil's law in this case is simply the statement that as the dimension of Hilbert space n tends to infinity, the phases of the eigenvalues, that is, the angles of these points on the unit circle, become uniformly dense. Yes?
What is the Fn inverse in front of your 3x3 matrix?
It's just the inverse of this Fourier transformation, of this Fourier matrix.
Okay, so on each diagonal, you multiply each diagonal by this?
It's an n dimension. It's the inverse.
Yeah, okay. It's the n-dimensional inverse of that.
N-dimensional inverse of that.
Okay.
It's also a Fourier. It's also a Fourier. Yeah, exactly. So the eigenvalues lie on the unit circle, and Weil's law is simply the statement that these equidistribute on the unit circle. So if I pick a segment of the unit circle of length L, then the number of eigenvalues in there is asymptotically L over 2 pi. Quantum ergodicity, which is proved rigorously for this class of maps, simply says that the eigenvectors of this n by n matrix, in the limit as n tends to infinity, when represented in phase space, for example via a Wigner function or a Husimi function, become uniform on the torus. So again, for this example, we see Weil's law and quantum ergodicity. Okay, so that's all I want to say about the background. That's what we know about closed systems. So let me just remind you what I've said for comparison later. I've told you that there's Weil's law. I've reminded you, this is very well known, that there's Weil's law, which says that the classical invariant set, the surface of constant energy in phase space, determines the counting of eigenvalues. So it's basically the volume of that contained within that set divided by Planck's constant to the d. D is the number of degrees of freedom. There's quantum ergodicity, which is that if the classical flow is ergodic, quantum eigenfunctions equidistribute on that classical invariant set, surface of constant energy. And I'll give you an example in terms of torus maps where one sees this rather explicitly. So now what I want to do is switch to open quantum systems. We already heard to talk about that just previously, and say what we know that's in those cases that's analogous to Weil's law and to quantum ergodicity. And the answer will be basically nothing. And I think this is remarkable, because Weil's law has been around for 100 years, and it's the most elementary thing you can ask about a spectrum. Quantum ergodicity has been around for over 30 years now, and it's the most elementary thing you can say about wave functions. And yet we don't know the analogues of those results for resonances. So, open systems. What are the resonances? Well, it's already been described to us. These are the poles of the green function, integral kernel of the resolvent operator, in the lower half plane, the imaginary part of z less than 0. So now we're in the situation where the resonances, where the eigenvalues are complex. And lie somewhere down there. And these resonances, these poles of the green function, have associated with them resonance eigenfunctions, which are governed by the residues at those poles in exactly the same way as the eigenfunctions in closed systems are given by the residues of the poles which lie on the real axis in that case. And these have been studied for a very long time. Within quantum mechanics, they were studied in the classic paper of Gamow on alpha decay. And since then, there's been a very extensive theory developed based on these resonance eigenfunctions and poles. Ziegert, Piles, many other people have contributed to this theory. So we have these resonances, and they lie in the lower half of the complex plane. And the analog of Weil's law, the Weil asymptotics, is if we draw a box in the lower half of the complex plane, how many resonances lie inside the box? How can we count the resonances? The analog of quantum ergodicity is, if we look at the resonance eigenfunctions associated with the resonances, how are they distributed in the semi-classical limit? Well, I've really emphasized that in the closed systems, what plays the role of supporting the eigenfunctions, the object that governs the distribution on the largest scales of the eigenvalues, is a classically invariant set. It's the set of points invariant under the classical flow, the largest such set, and that's the set of points lying on the surface of constant energy. So what in this case is the relevant classically invariant set? Sorry?
If you use the Klein-Biermann and take the determinant of S, the scattering matrix, then you do have a different counting of resonances,
yes,
which is completely analogous to the Weil formula.
That's true. That's true. But that's yes.
It's a different count.
It's completely different. Yeah.
Because you decided arbitrarily to put this particular line in the complex plane. If you have measured or you counted,
yes,
as you are told by Klein-Biermann, then you have analogy to that. So it is a question of what do you want to count.
Absolutely. No, I quite agree with that. It's a question of how you weight the resonances. And there are several ways to weight them. You might weight them with decreasing weight, a weight that decreases with their distance from the real axis. Physically, that's a very natural way to do this. But the other natural question is simply, if you don't weigh them, if you draw a box in the complex plane, how many resonances lie inside that box? So I absolutely agree with you. There are many ways, many questions you can ask. This is one of them. So what's the natural classically invariant set in this case? Well, it's what's known in classical mechanics as the strange repeller. It's the set of points in phase space that remains trapped inside the scattering region as time t goes to plus or minus infinity, so for all positive and negative time. First of all, first hearing about it, you might be surprised that there is a set of points that's trapped for all time, but one thinks just for a second and realizes that there are periodic orbits inside the scattering region which may not hit the openings. So they're certainly trapped for all time. And then these periodic orbits, if they're unstable, and that's the situation we'll be considering, exponentially unstable, they come with stable and unstable manifolds. So there are points on the stable and unstable manifolds which remain trapped for positive and negative time. So the strange repeller is the intersection of the backward trap set, that's the set of points that remains trapped as time t goes to minus infinity, and the forward trap set, which is a set of points which remains trapped in forward time. The intersection of those two is the strange repeller, and it's strange because if the dynamics is classically hyperbolic, then that set is a strange set. It's a fractal set in phase space. So the intuition, which started with Jostrand, I believe, and has been much developed by Maciej Zworsky and many others, is that for closed systems, Weil's law tells you to associate quantum states with the volume of the surface of constant energy. You count states by measuring the volume of the surface of constant energy in units of Planck's constant to the number of degrees of freedom. So since this is a fractal set, perhaps one should have a fractal Weil law. So perhaps the counting of resonances should have a fractional dimension of Planck's constant, and that fractional dimension is the dimension of the strange repeller underlying the classical mechanics. So this is an idea which has been around now for a few years, much studied numerically, even studied experimentally, but as I'll indicate, in not one single physical example has it been proved. And I think this is kind of interesting, that this Weil's law has been around for 100 years, and yet this analogue of Weil's law, one analogue of Weil's law, but a very natural one, is proved in no single physically realizable example. No billiard, nothing like that. No physically realizable example can one establish this, even though all the numerics points to its truth in experiments. So to give an example for billiards, if one has a billiard with openings, as I've drawn it up there, this says that if you count the resonances inside a box, exactly as I drew it on my previous transparency, so if one has a box where one fixes the depth of the box and lets the width go to infinity, the box is getting longer and longer, but the lifetimes one's considering are bounded, then the conjecture is that the number of resonances inside the box as a function of its length should scale as a fractional power of the length, where the fractional power is the dimension of the repeller. Now, which dimension is a key question, and I think I'd say it's not even settled completely at the conjectural level. Most statements would say it's the upper Minkowski dimension, but I think this is a matter of still some dispute as to precisely which dimension should go in the exponent there. Let me give you an example involving the Baker map, the map that I introduced earlier. We're now going to take our Baker map and make it open by taking out the middle third rectangle and calling that an opening. So any points that map into that opening are gone forever from the system, never to return. So as points map around on the torus, whenever they enter the region shaded red here, they're gone forever out of the system. So this is now an open system. Points leak out, and they do so exponentially quickly. This is a hyperbolic system. So exponentially quickly, volume escapes into the opening, and then disappears forever. So under the action of the map, this picture, as I indicated earlier, goes to this picture. We've squashed uniformly, stretched uniformly, and then rearranged the pieces to get this. And this picture then, if you map it again, so we've gone from this to this to this, etc. At each iteration, you increase now the number of bands by a factor of 3 and decrease the width by a factor of 3. So the trap sets in this case, the backward trap set is the original torus having removed all of the forward iterates of the opening. So you remove, so it's the original torus with this band removed, these bands removed, and all further forward iterates of these bands. So you can see that the backward trap set is simply the interval 0, 1 composed in the horizontal direction, and vertically it's the middle 1/3 Cantor set. Likewise, the forward trap set is the original torus with all backward iterates of the opening removed, and that's just in the vertical direction, the middle 1/3 Cantor set, and in the horizontal direction, the interval 0, 1. So the strange repeller in this case is the intersection of these sets. So it's a middle third Cantor set horizontally and a middle third Cantor set vertically. So just to show that with some colors, here's the original unit square. We take out the opening. This is now to reproduce the forward trap set. Take out the opening. We take out the iterates of the opening, backward iterates of the opening. First of all, the red, then the green, then the blue, then the black. Keep iterating this, and what one's left with is the middle 1/3 Cantor set horizontally and the uniform distribution vertically. So that's the classical dynamics. The quantum dynamics in this case corresponds to a matrix, an n by n matrix, which is the n-dimensional inverse Fourier matrix as we had it before, and it's now the block diagonal matrix as we had it before, but where the middle block is replaced by 0. The reason for that is that the opening, everything leaves through the opening. So we want to set anything going into the opening equal to 0. So we've gone from a unitary matrix to a subunitary matrix, which has just this structure. So it's the n by n Fourier matrix, a block diagonal matrix with smaller Fourier matrices in the top left and bottom right, and zeros elsewhere. And the conjecture is, and I think this is really rather interesting, this is a pretty simple matrix. It's just the composition of, it's just made out of Fourier block Fourier matrices. What could be simpler than that? Even in this case, one can't establish the fractal Weyl law. What is the fractal Weyl law? Well, it says that we have a subunitary matrix, so the eigenvalues lie inside the unit circle, and if one considers some annulus, doesn't matter what the radius of the annulus is, you ask how many resonances lie inside that annulus, then the number of resonances inside that annulus should scale as n, the dimension of the matrix, to the power log 2 over log 3. That's pretty simple. It's a pretty simple matrix, it's a pretty simple answer, but it's extraordinarily difficult to prove this. So I think it's a good problem.
Numerically?
Numerically, it's absolutely bang on. Absolutely bang on. So,
But we have no analytic tools for studying eigenvalues of non-normal matrices.
absolutely. Absolutely. And isn't it interesting that we're in that situation? But I'll show you a matrix that we can analyze later. So it's not completely hopeless. There's one case that we can study. So the question I want to address here is what's the semi-classical structure of the resonance eigenfunctions or eigenvectors? So in this case, this n by n matrix has eigenvalues, they're the resonances, and it has eigenvectors, they're the resonance eigenstates. What's their structure? So this is what I want to discuss, and what I'm going to do is give you a sort of general semi-classical expectation, so the sort of thing that comes from the sort of theoretical physics understanding of quantum chaotic systems. So I'll tell you what we think we know is true, but which we can't prove, and then I'll give you a more refined example where we can prove something. I'll give you some rigorous results at the end of the talk. But I warn you, they'll be rather modest. These are hard problems. So, general semi-classical theory. So here's the intuition. We have our subunitary matrix. Think of it as this block Fourier matrix. And it has right eigenvectors and left eigenvectors. Just for definiteness, I'll consider the right eigenvectors. Everything I say transfers immediately to the left eigenvectors. So I won't even bother to repeat that comment. So to consider the right eigenvectors, we'll represent those in the Husimi representation. That is, we'll take the overlap of a right eigenvector with a coherent state, sort of little Gaussian wave packet at some point QP in phase space, and take the modular square of that. Then what might we expect? Well, if we consider the kth iterate of our quantum map, subunitary, and sandwich it between a right eigenvector and a coherent state and take the modulus square, by definition, because this is a right eigenvector, this is just the corresponding eigenvalue to the power 2k, the modulus of that to the power 2k, times the Husimi representation of the right eigenvector. But if we fix k and take the semi-classical limit, we know that coherent states map classically. Little Gaussian wave packets move according to the classical mechanics. That's what quantization means in the semi-classical limit. So this means that if we pick a point that's not on the backward trap set, and we map it classically, it goes into the opening. So it's dead. So that means it makes no contribution here. So this tells you that the Husimi function, representing that right eigenstate, should be 0 off the backward trap set. So we have our backward trap set. It's this, in the case of the Baker map, it's a middle 1/3 Cantor set composed with the unit interval. And this kind of this semi-classical argument, this is the one thing I'll say here which can be made rigorous in general for the Baker map. So this is a rigorous statement I'm telling you here. The backward trap set, the resonance eigenfunctions, corresponding to the right eigenvectors, are 0 off the backward trap set. And in fact, for the Baker map, one can establish that off the backward trap set, they tend to 0 exponentially fast as n tends to infinity. So they have a fractal structure. The backward trap set is a fractal, middle 1/3 Cantor set, so the resonance eigenfunctions are fractal. We can say a bit more. Again, this is now non-rigorous what I'm telling you. I don't know how to make it rigorous. If we consider that pi 0 to be the projector onto the opening, and pi k to be the projector onto the set of points which fall into the opening after k steps but not before, well, just by definition of the original Baker map, the quantum Baker map that I wrote down for you, if we take that with it multiplied by its Hermitian transpose, that's just 1 minus pi 0. So if we take the overlap of this with the right resonance, right eigenvectors, we just get 1 minus the modulus square of the corresponding eigenvalue. If we consider this doing the same thing using the kth power of the if we consider the overlap with the set pi k, if we fix k and take the limit as n tends to infinity, because points map classically when we take overlaps with smooth eigenfunctions, these sets map classically. And so if we fix k and take the limit as n tends to infinity, it should be that the overlap of a right eigenvector with the set pi k, diagonal matrix elements of that, scale in this way. They have the modulus of the eigenvalue to the power 2k. This is just iterating this relation and this one here, and 1 minus the eigenvalue to the power 2. So what do we learn from this? Well, we've learnt already that no matter where you are in the spectrum, from this general argument, the Husimi function will be non-zero off the backward trap set. That's the most we can say in general. This argument suggests, if you look at it, that if you look at the edge of the spectrum, where the eigenvalue, modulus of the eigenvalue Zn tends to 1, this term tends to 0. So this overlap should tend to 0. But that's the overlap of the right eigenvectors with the set pi k, that is the set of points which map into the opening. So this says that anywhere in the bulk of the spectrum, the right eigenvectors, when represented in a phase-space way, for example by Husimi, are non-zero off the backward trap set. This suggests they're also non-zero off the forward trap set as you approach for eigenvalues corresponding to the edge of the spectrum near 1, that is with very long lifetimes. So at that edge of the spectrum, so in the bulk, the eigenvectors are non-zero off the backward trap set, are non-zero only on the backward trap set. Near the edge of the spectrum, for eigenvalues very close to the edge, taking a limit semi-classically as you approach the edge of the spectrum, they should also be non-zero only off the forward trap set, and so that is, they should lie on the classical repeller, the intersection of the forward and backward trap sets. So this says that the semi-classical structure depends on the lifetime, and this is no surprise, of course. The hard part of this problem is that whereas in closed systems one has only one parameter to deal with, that's the semi-classical parameter, here there are two parameters. There's the semi-classical parameter and there's the lifetime. And it's an interplay between those which makes this a hard problem. Anyway, going back to this formula here, which is a sort of approximation to which one can't really give error estimates, unfortunately. This also implies, and I won't go through the arguments for this, that if the decay rate, so if the lifetime is equal to the classical escape rate, the rate at which volume leaves the system classically, then the right eigenstates become uniform semi-classically over the backward trap set. I won't give you the argument for that, it's slightly involved, and I don't want to pursue it because I don't know how to make a rigorous statement of it. So we have these pictures. Now let me show you how they compare with what you actually see when you plot eigenfunctions. So this is the, oh my goodness, right. This hasn't done terribly well. Sorry about that, it looks good on my screen. This is the Wigner function. You'll just have to believe me. This is the Wigner function of eigenstates plotted in phase space. And what you see is that the Wigner functions show structure corresponding precisely to the middle one-third Cantor set. This is what I was arguing earlier, that in the semi-classical limit, resonance eigenfunctions live on the, in this case, the backward trap set, which is the Cantor set horizontally and uniform set vertically. This, which also is truncated, is the Husimi representation, which is just a Gaussian average of the Wigner representation. So one sees much less here, but in the Wigner function, one sees in quite a bit of detail the classical trap set. So the resonance eigenfunctions have this fractal form. This has come out slightly better, perhaps. If you project those pictures down onto position representation, this is a position eigenfunction plotted here between 0 and 1/3. And you see the eigenfunctions have structure lying on the Cantor set. If you explode this smaller region now, if you expand this region, so this is plotted between 0 and 1/3. If I simply take the range between 0 and 0.1 and expand it up, you see the structure of the eigenfunctions is self-similar. So one sees this self-similar fractal structure in the classical mechanics represented in the resonance eigenfunctions. If we project horizontally onto the momentum axis, one doesn't see the Cantor set, but one does still see self-similar fractal behavior, which I've not argued for, and which I don't have a general semi-classical theory for. But now here's the projection onto momentum. I'm sorry, that position is written there. That's an error. It should be momentum. This is a momentum representation of the same eigenfunction. It lives on the whole interval, not on a Cantor set. Lives on the whole interval, but it's still self-similar. Here it's plotted between 0 and 1/3, and here it's plotted between 0 and 0.1. So the structure here, this structure plotted here is this structure here magnified by 3. So in both directions, one sees this interesting fractal structure in the resonance eigenfunctions. Of course, this is why it's a very hard problem to analyze, because one has to combine, to really prove these statements, semi-classical asymptotics with fractal geometry. But there is one case where one can prove something, and this is what I'm going to explain to you, and it's, if you think quantum maps are a toy example and unphysical, I'm afraid this is going to get even more I don't know whether one thinks of it as an executive toy, which aren't real toys, of course, or a very cheap toy. So either end of the spectrum, I can't argue. It depends on your taste in toys. So this is the Walsh quantized Baker map. And this is the only case where one can prove these statements, to the best of my knowledge so far. So this isn't real quantum mechanics, it's mock quantum mechanics. And let me explain to you in what sense I mean that. We get you can only do this when the dimension of the Hilbert space is a power of 3. And then what you do is, you get the original matrix, which for the closed Baker map was composed of small Fourier matrices. It was Fn to the minus 1, Fn over 3, Fn over 3, Fn over 3. The open map corresponding to putting a 0 there, subunitary matrix. Now what we're going to do is replace the Fourier matrix, whose matrix elements I've written for you here, it's just the discrete Fourier transform, with what's called the Walsh Fourier transform. So you should think of this as akin to a wavelet transformation. So it has the flavor of a Fourier transformation, but it truncates in a way that is governed by the ternary representation of the row and column indices n and m in the following way. So here's a definition. We're going to replace the Fourier matrix by this matrix, by these matrix elements, where the nmth matrix element looks like the original Fourier matrix elements, but what appear instead of n and m are the components of the ternary representation of n and m. So I say this has the flavor of a wavelet transformation, and what it does in effect is for the Walsh transformation, the coherent states no longer have circular symmetry, they have rectangular symmetry. And this is the thing that will allow us to prove something, because the Baker map, when you're squashing and cutting, has rectangular, the cutting is vertically. And the problem with analyzing this rigorously is, if you start squashing and cutting circular coherent states, you start chopping them up, and it's rather hard to keep control over all the pieces. If your coherent states are rectangles, that's very easy, relatively easy. So we have this transformation. So in what sense is this quantum mechanics? Well, it's not quantum mechanics as Heisenberg or Schrödinger would recognize it, because it's not based on a Fourier transformation. The relationship between position and momentum isn't via a Fourier relationship, it's by this Walsh Fourier relationship. So it's a mock quantum mechanics, but it has all the mathematical structure of quantum mechanics. It's just easier to analyze in this context. So these are the matrix elements we're going to use now. The advantage of this is that position eigenstates become a tensor product of states just governed by the integers 0, 1, 2. So and the action of this matrix element, of the Walsh matrix, on the Hilbert space decomposes in this tensor product, and it's just given by the original Fourier matrix where n is 3. So we can deal with 3 by 3 Fourier matrices, and that's what allows us to prove something. So what I'm going to show you is what we can prove, and I'll state, so first of all, for this system one can establish rigorously the fractal Weyl law. It's actually rather straightforward, it turns out. One can calculate the eigenvalues explicitly, and they have a crystalline structure. So they're highly symmetric in phase space, and one can count them inside annuli, and one does indeed get the fractal Weyl. And this was proved by Nonomasher and Zworsky rather recently. What we know about, and this is the recent work I want to tell you about concerning the resonance eigenstates, we have 4 theorems. I'll state one theorem rather precisely. The other 3 are just technically involved to state precisely, so I'll give you the flavor of what they tell us. Theorem 1 is that if we consider a set of eigenstates of the Walsh Fourier map, so eigenvectors of the Walsh Fourier matrix, such that the eigenvalues tend to the outside of the spectrum, the outer edge, they tend to 1, that is, their lifetimes tend to infinity, then indeed the semi-classical expectation I led you to before is correct. The corresponding Husimi measures, weak star, converge to a unique invariant measure supported on the repeller. So one has not just quantum ergodicity on the repeller, actually we can establish unique quantum ergodicity in this case. So this is true for all possible subsequences of eigenstates where the eigenvalues converge to the outer edge of the spectrum. Now for the Walsh-Fourier matrix, it turns out there's an inner edge to the spectrum. So there are n eigenvalues. There's a non-trivial spectrum lying between 1 and radius 1 over root 3, and all the other eigenvalues lie at the center of the unit circle. So there's an outer edge and an inner edge. If we analyze what goes on at the inner edge of the spectrum, so if you consider a sequence of eigenvalues converging to the inner edge, then the Husimi measures weak star converge, again uniquely, to a self-similar measure supported on the backward trap set. So you see that where you are in your lifetime governs what the resonance eigenfunctions look like. At one edge of the spectrum, they lie on the whole repeller. On the other edge of the spectrum, they lie on the backward trap set. So analyzing semi-classically the structure of the resonance eigenfunctions, one has to control where one is in the spectrum. Different bits of the spectrum, the resonance eigenfunctions look different. Now we can establish that these unique measures, so we have unique ergodicity in both cases, and these unique measures can both be factorized as a Cantor measure, that is the uniform measure on the Cantor set, multiplied by a measure that's in the vertical momentum direction, multiplied by a measure in the horizontal direction, which in one case is also the Cantor measure, and in the other case, that is at the inner edge of the spectrum, is another self-similar measure. So this is exactly consistent with the numerics I showed you earlier. So at one edge of the spectrum, you can think of the resonance eigenfunctions as being uniform on the repeller, that is on the composition of a Cantor set horizontally and a Cantor set vertically. At the other edge of the spectrum, the eigenfunctions you can think of as being uniform on the backward trap set, which is a Cantor set in one direction and a uniform in the other, and in that direction, the measure is self-similar. So this is exactly consistent with the numerical pictures I showed you before. Now we have three more theorems, which I say I won't state precisely because they're technical and it's late in the day, but I'll give you a flavour of what they say, because they're rather interesting. They concern what happens in the bulk of the spectrum. And this is where things get really interesting, where we know very, very little. The best we can prove is that we know that the eigenvalues have a certain, they're highly symmetric for the Walsh-Baker map. And in particular, if you pick a circle in the bulk of the spectrum, there are many eigenvalues lying on that circle for most circles. In the semi-classical limit, that's certainly true. If you fix the dimension of the Hilbert space and average over the eigenvalues on a circle in the bulk of the spectrum, then the Husimi measure, weak star, converges to something which is a composition of a Cantor measure in the vertical direction and a self-similar measure in the horizontal direction, but a different measure depending on the radius of the circle. So the eigenfunctions look different depending on which point in the spectrum you're at, which point in the bulk. They change throughout the bulk of the spectrum. In the limit in the semi-classical limit, as the dimension of the Hilbert space tends to infinity, this is true at a fixed point in the bulk of the spectrum. So the first theorem concerns averaging over a large number of eigenstates for any dimension of the Hilbert space, but that happens to be true at any point on that circle in the semi-classical limit. So in that sense, the average is ergodic. And finally, all the measures I've shown you so far, all these limiting measures, are a composition of a Cantor measure in one direction and some other measure in the other direction. Is that true everywhere? Well, surprisingly, the answer is no. You can establish that there are points. We can't construct them, but we can prove that they exist. There are points inside the bulk of the spectrum where the limit measure is not of the form composition of a Cantor set and a measure in the horizontal direction. So what I think this illustrates is this is a very rich set of problems. The problems I think are very interesting. Our progress is rather minimal, but we do what we can. Thank you.
More a thought than a question. So, to perhaps get a lower bound of vial type in your non-toy problem, so you should be able to get good guesses for variational eigenfunctions. And Davis and I have actual results to go from variational estimates to eigenvalues. You throw away a dimension of the space, but since these estimates should be exponential, that dimension probably doesn't matter. And this might actually show the existence of eigenvalues where you expect them. That won't show that's all you have.
Right.
It should give you a lower bound. So I'd recommend you might want to look at this.
Okay, well, thank you. Yeah, I'd not thought in that direction.
Yeah, so what I've understood, what you've told us here, is that you expect to see some kind of well, I would call it scarring for the, and somehow we don't quite expect the same phenomena for closed systems. How do we reconcile the two pictures?
Well, the two pictures are that you expect the eigenfunctions in both cases to be supported on the relevant classical invariant set. For closed systems, the classical invariant set is some nice manifold, it's a surface of constant energy. For these open systems, the classical invariant set is a strange set, it's a fractal, and so you expect the eigenfunctions to be supported on a fractal. So I wouldn't call it scarring. I think it's ergodicity on sets of rather different types. It's very interesting then to ask what the small scale structure of these eigenfunctions is on the scale of a de Broglie wavelength or the analog for resonances, and we don't have even numerically, I don't know of any results in that direction.
Well, could you comment on the scarring? I mean, in the closed systems.
Yes. So in closed systems, scarring's related to this issue. Well, it depends precisely what you mean by scarring. The physicists and mathematicians have different notions of scarring, but in the very strong sense, that is where you have a sequence of eigenstates which semi-classically converge onto a measure that's supported on a periodic orbit. One can establish in some systems, so this is the issue of unique quantum ergodicity, one can rule out scarring in many systems now, but for some systems one can prove that scarring really occurs. And it's not at all clear how one reconciles these, that is, it's not clear from these theorems what the conditions are which give rise to scarring in some cases and not in others.
For which systems do you have scarring in the classical limit?
Cat maps.